Chapter 7, Scatterplots, Association and Correlation. So scatterplots are the best way to see relationships in data. We look for possible association, when examining a scatter plot, look at, so similar to how with the last one we had like shape, center, spread, outliers, or we had our socks, we have similar kind of thing. It's not, there's no acronym to help you remember it, but it's the same principle. We're looking at direction, meaning is it going negative, okay, in terms of slope, or positive. We want to look at the shape of it. So in this sense, when we're talking about shape, we're talking about, is it linear? Is it curved? Is it like random, just all over the place, etc.? So we just want to describe it the best that we can from that. And then the strength. We want to talk about if it's strong, weak, or moderate. And then we also want to mention any outliers when we're talking about strength, because sometimes they will still exist here, or it'll be like all your data is in this little area and then there's just one dot like way out somewhere, and so we just got to be aware of that. So I'm going to draw two scatter plots, and then I'm going to write a little bit beside them of like how we would describe them with this information. So all right, so this first one, it's going to be like that. Next one. And these are in like no particular order, it's just sporadic. I'll let y'all draw those and then we'll talk about them. And when we do, like, actually when you're like drawing scatter plots and stuff like that, if you want to use like a marker so that you can see it better, if you don't have markers, I have some that you can use. Last year they like, sometimes they couldn't see them like when they would do something, so I would be like, here, just use this and whatever. But anyways, all right, so this one, okay, let's go down in order. So direction, are we positive or negative for this first one? Positive. And then I'm gonna jump down and I'm gonna do strength next because I'm gonna show you how I'm gonna write exactly how, like, what I would say. So does it look like, so with strong, we're talking about things that are really tight together. Weak would be very, very spread out, and then kind of still looking organized, but a little bit more spread out is what we would call moderate. So what do you think this one would be? Yeah. So we would say a strong or sometimes moderately strong, like it's going to sound kind of crazy, but you can have like a mixture of the two. So I would say strong for this one. Sometimes people will only say strong if they're like exactly in a line, but and then what kind of shape? Are we linear, curved, random? Linear. So I would say in this case, I would say this is strong. So a strong, positive, linear relationship would be how we would describe that one. What do we think about the second one?
I would say it's weak.
Yeah, weak.
Negative.
Yeah. Weak, negative, linear relationship. All right, so then just some information about these. The variables that go on the x-axis are the independent. See, it's coming back now. It's not just in science anymore. The independent or predictor variables. See, now when I ask what kind of variable it is, you can actually say it's independent or dependent. I'm not looking for categorical or quantitative now. I used to be so bad at that. Like, it makes so much sense, but I used to be so bad at saying if it was the independent or dependent variable.
I'm still terrible at it.
Yeah.
Good thing I'm not in science.
I know, people are like, what's the independent variable? I'm like, I don't know. I'm like, what's changing? It looks like 5 things are changing. That can't be right.
Yeah.
All right, and then the other one is the response variable. Or dependent. Typically, they're going to say predictor or response variable, I think, in this book, but independent, dependent, I will know what that means. It is a little easier to tell in math than it is in science, just in case you're concerned. But the response variable is the variable on the y-axis, or the variable of interest that goes on the y-axis. All right, the next thing is correlation. This measures the strength of a linear association between two variables. It is a more specific definition in stats than the general meaning of correlation. So in a sense, like things like what that kind of is talking about is like in a sense, like things can be like correlated, like you coming to school because it's a weekday, like those things can be correlated, but like in like stats, it's like, well, I don't know, I'm trying to think of a good example. You ate a lot of food, so you gained weight. I don't know, like things that like different things, but it's gonna make more like how strongly correlated are those things is why. I don't know. That was a bad example, but whatever. I tried. Let's see. Joelle, I think when we were in pre-cal, I think we talked a little about a correlation coefficient briefly. We did, it's the R value. Ethan, have you done correlation coefficients before? In terms of like when you're doing scatter plots, have you done anything with that before? Okay, I was just curious because we like briefly touch on it, just like if you're gonna take stats, here you go. Okay.
I never took a props or stats class.
Well, yeah, I mean, we just touched on it a little bit in Algebra 2 and a very little bit in pre-cal, so that's why I was just curious if you had touched on it at all. So the correlation coefficient and that'll be symbolized by a lowercase r. I don't honestly know. But the correlation coefficient gives a numeric value for the strength of the linear relationship it ranges from +1, which is for a perfect positive relationship, to -1, which is for a perfect negative relationship, and then a correlation coefficient near 0 indicates a weak, or sometimes we would say no evidence of a linear association. So basically, the closer it is to 0, either positive or negative, the weaker it is. The closer it is to 1, either positive or negative, the stronger it is. Now, something to note here specifically is that this part right here, when it's talking about the linear association, this does not mean there is no relationship. It only means that there's no linear relationship. So there's different kinds of relationships that we can have. There can be like, well, curved, whatever, but when we're talking about correlation coefficient, we're talking about linear. So also like with the normal model, there is some conditions that we have to check to see if like it works or we can use it. So correlation conditions. So we need to check the following. It's going to be 3 things. 1, we must have quantitative variables. Okay, I think we had that problem with, what was it, hair color and eye color or something like that. And it wanted to know the correlation of those 2 things. And that, like, those were categorical variables, so that was why we couldn't do that. So they have to be quantitative. It's got to be a straight enough scatter plot. So in terms of, like, it needs to be basically pretty linear looking. It can't just be like all over the place and sporadic or curved or whatever. And then 3, no outliers. And so sometimes we'll just remove the outlier entirely because that can completely throw off our correlation. And eventually we'll talk about where the outlier sits for what effect it has on the correlation. And we check all of these by examining the scatter plot. So these are all checked by examining the scatter plot. Whoa. So the good news is the correlation coefficient is found on your calculator, so you don't have to do it by hand. Essentially, we're looking at, I mean, it's kind of like the slope value is kind of like what the correlation, in a sense, will make you think of. It's not necessarily the actual slope value of the line, but that's how I would think about it. So you can calculate the correlation coefficient for a set of data using the linreg command on the calculator. And you'll find that under, what is it, stat, calc, and then you'll look for linreg. There's actually 2 linregs, because we were actually talking about this a little bit in pre-cal this morning. It technically doesn't matter, but I always use the AX plus B one. Or I should say almost always use the AX plus B one, but when we get to examples and stuff, we'll see more of that. So then just a couple things to note about it. The sign of a correlation, okay, in terms of positive or negative. But the sign of the correlation indicates the direction of the association. So that's kind of what I mean about the slope, like if it's positive or negative. That's more so where I was going with that. It's always between -1 and +1, and it's rarely exactly -1 or +1. Correlation is the same for x to y as y to x. Correlation also has no units. Variables can have a strong association below correlation value if the relationship isn't linear. And then, like I kind of mentioned earlier, correlation is sensitive to outliers. And then something just really important to note is that correlation is not equal to causation. And I'll show you an example of that in a minute, but we can only describe association by saying increased variable x is associated with increased or decreased variable y. So, like, what's happening is x gets bigger, basically. Be aware of lurking variables. So these can be things that aren't necessarily mentioned, but are definitely a factor, or sometimes things that are factors that don't have anything to, or like that are mentioned but actually don't have anything to do with it. So just be aware of those. And again, with the examples that we do, it'll make more sense what all these things actually are. So a good correlation statement, because we always are going to need to wrap up whatever we say with some kind of a conclusion statement. So a good correlation statement, I'm going to tell you what a good one would say, and then I'm going to tell you what something that would be a assuming causation would say. So the first one, there appears to be a strong positive linear correlation between hours studied and test scores. Students who studied longer tend to have higher scores. Now, something that we wouldn't want to say, don't assume causation. By saying if a student studies for more hours, their score will increase. So just because the evidence that we were given says that the students who studied longer got a better test score does not mean that that is always the case. So that's why we can't say, oh, well, if you study for more hours, then you're going to get a higher test score, because that's not necessarily true. So no causation. And like things like with a lurking variable with this particular one, it could also be, you know, how much they paid attention in class and things like that. So there's other things that can affect this, which is also why we don't want to say what I wrote here in purple. So, but that's all the notes. So we'll pick up on Tuesday with examples.